In the first job I ever had about 40 years ago, my first task was to try and track down some sporadic issues caused in a digital system. It turned out to be noise on the various buses in the system. And there's various different types of noise you get on these systems, but it was very interesting work, and I find myself here 40 years later doing the same thing again. This time it's on an Altair. This is obviously an Altair 8800. I'm sure that anyone that's owned one of these or owns one of these is familiar with the problem, and that is the backplane is very noisy. I kind of hesitate to say or use the word noisy. It's not really noise. There are various things that are causing problems on this machine when you plug various cards in. And over the last 18 months or so, I've spent quite a lot of time investigating what's causing this. In the next few videos I want to just go over what I've found so far. Anyone that's found different things or can add to what I'm saying, it would be greatly appreciated by myself, and I'm sure by any other Altair users that are struggling to get some of these machines to work reliably. The findings I've come up with so far fall into several categories. The first thing to understand if you're not familiar with digital systems is that the noise is not caused and is not really influenced by the frequency that the clock is running at. So this particular machine runs at 2 megahertz. It doesn't really make any difference if you go up to 4 or 6. Now it can be confusing because going to higher frequencies the problem may seem to get worse, but as I go through the video hopefully the reason for that will become clear. It's more to do with the current state of data on the various buses and control lines rather than the clock frequency itself. Dave Jones on EV blog has done some fairly good videos about the difference between frequency and the edge rate in a digital system. So that is to say that the highest frequency on a digital line is caused by the rate of switching of the line, not by the period of switching. So you can imagine a square wave as really comprising of a large number of sine waves with a fundamental sine wave frequency and then all the various harmonics superimposed. And it's the highest frequency harmonics that you're looking at that cause problems in a digital system, or that's usually the case. So in this case, one of the first things I'm going to look at is why it's so difficult to decide where to place cards in this machine. Now I'm using this particular Altair because it's got a very old 18 slot motherboard, and this is by far the worst machine I have with regards to exhibiting noise on the bus. Again, I'm using the term noise to talk about various things or to encompass various things, but I will separate them as I go through the various videos. Now the biggest problem, the fundamental problem, comes down to the basic design concept for the Altair, and that is that this is the schematic for the CPU board. I don't know how well this will come out on camera, but there are various problems with this that can seem to manifest themselves as motherboard noise, but it's not actually caused by the motherboard. So the first one of these problems we'll look at is the data bus and the various things and weird effects you see on the data bus. And I've got the scope hooked up. It's actually hooked up to data line 7 on the memory card, and this card is about a quarter way down the motherboard, just an arbitrary position to give some example as to the signals we're going to see. And the problem that we're looking at here is when we capture data, we're looking at data coming out of the data bus going onto the main backplane. That's what we're monitoring on the scope. So if I capture a signal on the scope, I'll do a one shot and I'll deposit some data into memory, and hopefully this is coming out on camera. If I set the cursor to the bottom of this secondary spike, so this secondary spike shouldn't be here. What's causing it is noise on the CPU card. It's not ringing, it's not noise, it's actually an active signal coming out of the card. And the reason it's doing that is because we have the main CPU here putting out data onto its data bus, and it's writing that data that's going to various places, including through these buffers to the actual backplane and then onto the various cards, which is the signal we're capturing. But it also goes directly out through this connector, which is this connector, and that goes out through to the control panel. These are really long cables, and it varies from machine to machine depending on exactly how these cables are bundled. But what's happening is the very sharp rising edge that we're getting coming out of the processor is going down these lines, very long cable, and then it's reflecting back as ringing and noise on this line. And also that can't really directly get through this chip, but what it is doing is the amplitude of the ringing is sufficient that even though the processor has finished switching, the ringing is causing this to switch on and off. So in other words, the input to the data lines going into the buffer is being affected by the reflected signals coming back from the control card. And you can, if you actually monitor the data going into this, you'll see severe ringing with one particular very high spike, and that is what is causing the output to switch back off. Now unfortunately, depending on the timing of the various cards that are installed and where they are on the motherboard, you can have a situation where while the card is supposed to be reading a high level, it might well be fooled into reading a low level. Had there been a buffer here, then that would be completely eliminated, and in fact, as I say, as I go through these various videos, I'll show some modifications I'm going to make to this machine to try to completely eliminate this problem. I won't be able to eliminate the noise completely, but if I can get to the point where it is invisible to the machine, then that is what I'm aiming for. So as I said, if there was a buffer here, then we wouldn't have this, because the reflected ringing wouldn't get through back onto this part of the data bus. So I'll be trying that in the next video, but for this video there are other ways to reduce this, and the first thing is to cut to these wires here. Now obviously that's ridiculous, we can't do that, it wouldn't work, but there is a way to effectively do that from the high frequency point of view without actually cutting the lines. There are other things that could be done, of course, but in this case the easiest way to get rid of this high frequency is to put a damper on this particular bundle. So if I capture the data again, we'll just do a few to make sure that we're getting a consistent result. So hit the deposit key, you see that we're getting quite consistent results. It's up around the sort of 300, 400, 500 millivolts. And it's going as low as 0, so we'll get, sometimes it will go right down to 0, and it's the nature of noise in that it is fairly inconsistent. And as you can see, this would most certainly cause a problem because you're well into the low value for the input to any gates, irrespective of the type of chip. So I'll do a few more just to get a good idea as to what we're looking at. And again, here we'll actually be below 0, so we're minus 400 millivolts. That's how severe the ringing is. So as I said, this is the output onto the motherboard. This is not the CPU card, but this is an active signal that's being created that we don't want. Now, one way we can reduce this is to try to effectively sever this line with regard to RF. That is this bundle of wires. So what I'm going to do is put a ferrite core onto it, just clip it on, and I'll do the same thing again. I haven't made any other changes, but already you can see that we are significantly higher than we were. We're up near 800 millivolts now. So we've improved the problem by the best part of half a volt, or in terms of the lowest signal we're seeing, which is the problematic ones. We're now 1 volt less noise, and that is a very significant thing. And in fact, if you're using Schmidt trigger buffers on the input to your cards, then the switching point for those gates is about 0.8, 0.9 volts, so we're already now outside of the problem area. So I'll put a second core on. And we'll capture some more signals. So as you can see, we've now got even more overhead. And we're now well out of the range of the switching for the input to the memory chips on the boards. So although I've made no other changes to the Altair other than just fitted a couple of ferrites to here, it has completely eliminated the problem of switching noise going into the memory cards. It does vary across the motherboard, so it's really picking a value for this particular inductor that will give you the best results. And on this particular machine, I found that for balance across the entire board, then just one of these is sufficient. Although you can't see them, I've also done the same thing on the power lines coming from the power supply. So I'm reducing any tendency for noise to echo up and down the lines. And I've also fitted another one of these to the bundle of wires that go from the edge of the motherboard to the control card, and that immediately eliminated a lot of problems I was having with this machine. And it does the same thing, it prevents noise bouncing up and down these very long wires. Some of these wires go from right at the back of the edge connector, right the way to the front of the machine, up the height of the machine, and all the way across the front, and they're nearly 1 meter long. And the CPU card is sitting at the end of that, and then going the other way you've got the entire length of an 18 slot motherboard, and this is why it causes so many problems. So this is kind of step one, is to understand that this spike is not just noise, it's the result of noise, and it's actually caused by a buffer switching when it shouldn't do on the CPU card. And although it's still doing it, it's a very short duration switch now, and it's been reduced, at least on this machine, to the point where it's totally preventing problems with the memory cards. I was having a problem when I was plugging in subsequent memory cards, and that the ones that were further away from the CPU wouldn't work reliably. Whereas fitting just one of these to this line has completely cured that. Other things I've done on this particular machine is I've actually cut the data lines on the underside of the motherboard and inserted 100 ohm resistors. And I did that halfway down the motherboard. It won't affect the integrity of the signals that you want, but it does have a tendency to reduce the actual ringing and noise on the motherboard itself. You still get ringing and noise on the motherboard. This won't cure that. This is just to prevent this particular problem, because this was such a severe problem on this machine that it kind of swamped everything else. But now that this is cured, I'll go on and look at finding ways of preventing ringing on the motherboard. Having said that, the next step is to try putting a buffer in these lines and see if that will completely eliminate this, which is what I'm aiming for first, because this, as I say, does present some fairly significant problems. If you want me to look at any particular aspects of this problem, then please drop a comment. I will be sharing the results as I get them, and as I say, the ultimate goal is to try and get an Altair that's reliable without completely replacing everything. I want to keep it as original as possible, but I do want it to work reliably, and I'm sure that everyone that owns one of these wants the same thing.